Hello everyone. To start off, we're just going to finish up the last section that we started what feels like a long time ago. But if you remember, the last time we met, we were talking about the chain rule. There's just one last thing to finish up in this section. If we go further back to the previous lesson on partial derivatives, we did this example in class where we had x cubed plus y cubed plus z cubed plus 6xyz equals 1, and we wanted to find these partial derivatives, so we had to use implicit differentiation. I'm going to go through exactly what we did in class again, and then we're going to talk about a new method to solve this problem. So what we did in class, if I want to find, for instance, the partial derivative of z with respect to x, where we don't have z equal to an expression, it's integrated into the expression, we're going to take the partial derivative with respect to x of this entire expression. Whenever we come to a y, it's going to be treated as a constant. Whenever we come to a z, we're going to differentiate implicitly, which means that, for instance, if we just go through here, we take a derivative with respect to x, we get x cubed becomes 3x squared, y cubed is 0. We get to z cubed, I take a derivative of z cubed, which is 3z squared, and I multiply by the partial derivative of z with respect to x, as we do in implicit differentiation. Now when I get to the term 6xyz, I have to use the product rule. One term, 6yz, comes from taking the derivative with respect to x, of x with respect to x, and this term 6xy times the partial derivative of z with respect to x is what happens when we take the partial derivative of this z term. We don't bother taking the partial derivative of y because it's just a constant, so we could add a 0 there if you want. This is exactly what we did in class. This should already be in your notes. From here is just a matter of grouping like terms. So here I've grouped the terms with the partial derivative of z with respect to x on one side, and I've subtracted the other terms to the other side, and then I divide by this term to get the answer. We could also divide everything by 3 since I can factor a 3 out, and this is what you would get here. I'm not going to go through the details of finding the partial derivative of z with respect to y. It's very similar, and we already did it in class, but this is the answer you would get before we factor a 3 out. Now what I really want to talk about today is a new method for doing this. And this new method requires you to rewrite this as an implicit function equal to 0. So what does that mean? That means you just get everything on one side of the equal sign. Now if you can write your function this way, we're saying that none of these variables are necessarily a function of each other, but we have some function that's a function of all of them. If I write my expression in this way, and let's say I want to take a partial derivative of z with respect to y, this formula says that it's equal to minus the partial derivative of this new function, capital F, with respect to y, divided by the partial derivative of this new function f with respect to z. Or written with subscript notation, which just makes things a little simpler to read. This is the exact same thing. It's just saying negative partial derivative of f with respect to y divided by partial derivative of f with respect to z. Now notice in the denominator, this is what we want to take the partial derivative of. We're trying to take the partial derivative of z. And up here in the numerator, we have a partial derivative with what we were taking the partial derivative with respect to. Again, we want to find the partial derivative of z with respect to y. So what we do is we take two partial derivatives of this function, and we take the partial derivative of that function with respect to y, divide by the partial derivative of that function with respect to z. So what happens is these two variables switch places. And that's always going to be the case. If I want to find the partial derivative of z with respect to x, then I take the partial derivative of this f function with respect to x, divide by the partial derivative of this f function with respect to z, put a negative out front. And the same is true for the partial derivative of x with respect to y. I get minus f sub y over f sub x. And again, these are both partial derivatives. So the variables just switch places. Now before we go back and do this example again, using this new method, let's just get an idea of how that works and how this is is this different from what we did before? And it's really not. Because if you look at what we did up here, basically these terms that I've gotten on this side are the partial derivatives of the terms up here with respect to x. And these terms, where I factored out a partial derivative of z with respect to x, are what you would get if you took a partial derivative here with respect to z. And you see we end up dividing, and there's a minus here because I subtracted these terms. So really it's the exact same thing. It's just an easier way to write this, and you won't have to worrying about this implicit differentiation anymore. So to see that, we're going to use this same equation way up here, x cubed plus y cubed plus z cubed plus 6xyz equals 1. And now we're going to find a new partial derivative. So using that equation from the last example, find the partial derivative of x with respect to y. The first thing we want to do is write this as an implicit function equals 0. So for this example, all that means is I subtract 1. Once I subtract 1, now everything's on one side of the equal sign. This is my capital F function. Okay. So now if I want to compute this partial derivative, I need to start computing partial derivatives of this capital F function. Since I want to find the partial derivative of x with respect to y, I'm going to find the partial derivative of this capital F function with respect to y and the partial derivative of this capital F function with respect to x. So the partial derivative of f with respect to y, these are just the same thing, different notation, right? I go back here and I say, okay, just find all the terms with y's, take their partial derivatives. If there is no y, we treat that term as a constant, so its partial derivative is 0. So if this has a term, so we're going to get 3y squared, which is where this term comes from. There's no y here, so that becomes 0. And here I have 6xyz. I just take a partial derivative with respect to y, that becomes 6xz. So the advantage here is I don't have to worry about using the product rule. I don't have to worry about the actual implicit differentiation. I'm just taking a partial derivative, which is much easier. Now I also need to find the partial derivative of this function with respect to x. So when I do that, I get 3x squared, this becomes 0, this becomes 0, this becomes 6yz. And of course this negative 1 is, you take a derivative of that, it's always going to be 0. So if I take this sheet away, this is what we have. That's exactly what I just said, 3x squared plus 6yz. So these are the two partial derivatives of that capital F function that I needed. So then to write my answer, I just put a negative out front. The partial derivative of that capital F function with respect to y over the partial derivative of that capital F function with respect to x. And then I can factor out a 3. And really these are both the same thing. Now, if I only have two variables going on, so in that last example we had x, y's, and z's. If I only have x, y's, for example, and I can still get everything to one side of an equal sign, then I can compute ordinary derivatives using the same method. So if I have f of x, y equals 0, I can compute not the partial derivative anymore, but the derivative of x with respect to y in the same way. It's just minus, now these are still partial derivatives, the partial derivative of f with respect to y over the partial derivative of f with respect to x. Now, why the difference? Well, what we're doing when we define these variables implicitly is when I look at this, I'm saying, okay, I want to take a derivative of x with respect to y. I'm thinking that x is some function of y. Since I only have two variables, if I think of one variable as a function of the other variable, that one thing, so if I say x is a function of y, there's only one variable I can take derivatives with respect to. So that's an ordinary derivative. Now, these are partial derivatives because f, as I've written it, is a function of two variables, so those have to be partial derivatives. I can also define the ordinary derivative, the derivative of y with respect to x. Again, we think of y as a function of x, it will be a function of one variable. So I can write that as minus the partial derivative of x, f with respect to x, over the partial derivative of f with respect to y. It's really the same rule, it's just now we have ordinary derivatives. So really what was happening before, when I had a function of three variables, and I'm trying to do this implicit differentiation, I'm saying that, for instance, up here, where I wanted to find the partial derivative of x with respect to y, since I had three variables in this function, I'm thinking of x as a function of y and z. So x itself was a function of two other variables, the other two. So I can't take an ordinary derivative, it has to be a partial derivative because it's a function of two variables. Okay, all of these formulas are a result of the implicit function theorem. Again, they're implicit functions. I'm thinking of x as a function of y or y as a function of x, but they're not explicitly solved for that variable. I don't have x equal to some expression. I just have an expression with a bunch of terms equal to 0. So it's not an explicit function. It's not saying x equals something of y times something of y, etc. It's implicit. We're not going to go into the details of the implicit function theorem. They talk about it briefly in the book. The details, they get more abstract than we need. So let's do a couple more examples before we finish. First, let's look at an example of a function of implicit function of two variables. So here I have 3x squared plus 2xy plus y cubed equals 6. I want to find the derivative of x with respect to y and the derivative of y with respect to x. And again, these are ordinary derivatives because I only have two variables here. So you can think that for this one, for instance, if I want to find the derivative of x with respect to y, what you could try to do is solve this for x and get x by itself and then just take a derivative. That's going to be very difficult to do because of this term 2xy. So instead, we can use these formulas from the implicit function theorem, write this, get everything on one side of the equal sign, so this is going to be my capital F, and now I start taking partial derivatives of this capital F. So if I take the derivative with respect to x, this becomes 6x, this becomes 2y, these both become 0. I take the partial derivative with respect to y, this is 0, this is 2x, this is 3y squared, this is 0. So I get that partial derivative. And then the derivative of x with respect to y is minus the partial derivative of f with respect to y over the partial derivative of f with respect to x. And so I get this expression. And then if I want the derivative of y with respect to x, I don't need to do any new computations. I just need to flip what I have here. And you see that's exactly what I get. Okay, the last example is similar to the first example we did. So now we have an expression that involves three variables. I want to find two partial derivatives, the partial derivative of z with respect to x and the partial derivative of z with respect to y. So one way you could try to do this is to solve this expression for z. You'd have an explicit function of x and y, but that's going to be very difficult because of these terms. You could do it the other way, where you go through and just differentiate implicitly, where you end up with using product rules and writing partial z's over partial x's everywhere. Or we can use this new way using these formulas where I get everything on one side of the equal sign. This is my capital F function. It's a function of x, y, and z. And then I'm going to go ahead and take all three partial derivatives all at once. So the partial derivative of f with respect to z is 3x squared plus 3y plus 6z squared, and that's coming from this term, this term, and this term. The partial derivative with respect to x, I get 6xz minus 2xy squared. And the partial derivative with respect to y, which you can see took me 2 tries because I forgot to write this squared when I copied the problem down. Oh well. Is negative 2x squared y plus 3z. Now, I've basically done all the hard work. All that's left for me to do is combine these in the correct way to represent the partial derivatives that I want. If I want the partial derivative of z with respect to x, then I take the partial derivative of capital F with respect to x, that's my numerator. The partial derivative of f with respect to z, that's my denominator. Make sure you put a minus out front, and that's my answer. I do the same thing for the partial derivative of z with respect to y, and here, since I have this minus 2x squared y in front, I didn't want these two minuses, so I just distributed this negative sign to these terms in the numerator, and that's what you get. Of course, there are many ways to write these things. You can rearrange the terms, distribute a negative to the numerator or the denominator, but not both, because if you distribute a negative to both, you've multiplied by a positive one, not a negative one. Okay, that's it for now. See you guys later.